So let me give you some hints for 1B. So if you start out with the geometric series, which is a power series. Now we know this is true for x between -1 and 1. So one thing you can do is you can think about this left-hand side. This is useful. Think about it as 1 minus x to the -1. So if you do that, then when you differentiate it, so when I differentiate, I get 1 over the quantity 1 minus x squared. And then this is 0 plus 1 plus 2x plus 3x squared plus ... And of course, we know that this has to be true between -1 and 1. Make sense? Okay, now do it again. So this time, you have to repeat the differentiation. So let's repeat. So what is this? Well, this, you could think of this as 1 minus x to the power -2. So when you differentiate it, or you can use the quotient rule, doesn't matter. You get -2 times everything. So this becomes 2 over 1 minus x quantity cubed equals 2 plus 6x. What's the next? What would the next one be? Well, the other one would be 4x cubed. So it's going to be 12x squared, etc. And that's between -1 and 1. And then the only thing you'd have to do is divide everything by 2. And that gives you the desired series. Does anybody have a question about this? Comments, concerns? Say that again. What do you mean it becomes x cubed? I'm confused. What's x cubed?
How did you get?
How did I get this?
No.
How did I get this? Differentiate. What's the derivative of 2x? 2, 6x. Huh? Take the derivatives. Take the derivatives. Yeah, give me 1 second. Trying to hit the wrong button. Hold on. This? Let me know when you're ready. Good? Emily, you good?
Yeah.
Good?
No, wait.
Wait, did you say no?
You said let me know when you're ready.
Oh, I thought you said okay. Sorry.
Oh.
Oh my Lord. These stupid masks. About to rescind. I'm gonna have to say. Does anybody have a question about this so far?
Didn't you say you were putting a quiz up or whatever?
Yeah, I will, but it won't be due. I'm going to put it up. I said I'd do it last night. It'll be due next week. You know, I'll give you plenty of time to do it. I think we need what? We had a quiz up to 11, right? So we need what, 15 more quiz points. So we'll just give it to you. Trying to make your life easy on you. You said you're done now? Oh, good. All right. Does anybody have any questions about this? So all you have to do to finish this is divide everything by 2. You get 1 plus 3x plus 6x squared. Fun times. All right, now the one that's the most difficult, and it's not that it's the most difficult, it just requires the proper steps, is part C. So part C, we have to be sort of clever. So you have 1 over 1 minus x, which again we know is x, 1 plus x. Yes, plus x squared plus x cubed plus dot, dot, dot. And of course, this is true for x between -1 and 1. Now, this implies that I'm going to replace x with 4x. So this is 1 minus 4x. Yikes. And so this is 1 plus 4x plus 16x squared plus 64x cubed. Now, you're not going to be as fast as me, so don't try to be as fast as me. You're a little amateurs. You're not supposed to be as fast as me. And the learning is really, you know, where you really make sense of all this is not right now, but if you would have tried this before you got here and then now you see it, and now you're like, then you have an aha, an epiphany. All right, now I need to integrate this. So let's go slow. I can integrate both sides, and we know now this is the left-hand side is probably not as obvious to you. You have to be a little more careful than I have to be. This integral requires a substitution. Right? And when you do a substitution, your u is 1 minus 4x, and so your du is -4. And so if you do the substitution correct, what you end up getting is this is -1/4 the natural log of 1 minus 4x. And then on the right side, it's x plus 4 over 2x squared plus 16 over 3x cubed plus 64 over 4x to the 4th, etc. And then, of course, you have a plus c. And the only place we know this equation is true is between -1 and 1. Now, we're not done, but we're almost there. All we have to do now is multiply both sides by -x squared, and you're done. By the way, it's important you also understand that notice 0 is inside the interval of convergence. 0 is between there. So if I plug 0 in, I get 0 equals 0 plus c, so that tells me that c has to be 0. So set x equals 0, and you get that c equals 0. And so to finish, I'll let you do it. Multiply both sides by -x squared. And then that gives you what you wanted to do. Say that again. Would I explain what? Yeah, so that's exactly what I'm saying. Put x to 0. What happens to the left-hand side when x is 0? What's the left-hand side? Say that? Yeah. And when x is 0 on the right-hand side, what do you get? Well, you get 0 plus c. So so if you have 0 is equal to 0 plus c, so c has to be 0. Does that make sense? Yeah. Now let me before we go any further, let's look at an application of this. sort of idea. So you might ask yourself, why might we care? Excuse me. To write. So this is a very natural question. You might say, well, why would we care to do this? Well, there's lots of reasons, but one is it makes other calculations easier. So one reason is that it can make other calculations easier. So now your argument might be though, so Emily or Shobit, you might say, well, what do you mean? That was a lot of work to get there. But the problem is if you build up a library of known power series, you don't have to do work. It's not difficult once you know the power series. You guys look at 4C and you're like, oh my God, that's ridiculous. But if you understand what the power, what the power series is for log, it's not ridiculous. It's actually quite easy. So we're going to give you an example of what we mean by this. So if you know the basic series, I'll put that in quotations because what I might think are basic, you might not, but there are certain power series you should know. I need to like blow my nose or something. I feel bad. Clogged up. So you should know some basic series. So you should know e to the x. We've written this down a bunch of times now. You should know this. You should know the sign. What's that? I don't need to. What's 2 factorial? And forget to. It's redundant. You could though. No, it's not wrong to do it. It's just redundant. That's why I don't do it. But I'm with you. Maybe I should so that it's a little more obvious to some of you. So if you know these guys, etc., I'm not going to write them all down. We wrote a few of them down. Then many limits, derivatives, integrals become trivial. Now, trivial is a bad word, but because I don't mean they're easy, but they become sort of less work. So let's look at an example of how this can be done. So let's take the limit as x goes to 0 of the sine of 5x over x. Now this integral is not difficult to do using Calc 1 stuff. And you could do it that way. However, I'm using this as an illustration of how power series can be used. So note, sine of x, as we know, is x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th, etc. This implies that the sine of 5x is 5x minus 1 over 3 factorial times 5x cubed plus 1 over 5 factorial times 5x to the 5th. Okay, so now if I take both sides and divide it by x, I'm left with 5 minus, what's 5 cubed? Well, that's 125 over 3 factorial x squared plus 5 to the 5th. I don't know what it is, and I don't care, frankly. This becomes x to the 4th minus. The main observation here is that on the right-hand side, every term except the first one has a power of x. Every single term. And so if I replace the right-hand side, if I plug x equals 0 in, the only thing that survives is 5. And so that tells us that the limit is 5. So let's write that down. So when I plug in 0, I get 5 minus 0 plus 0 minus 0 plus 0 minus 0 plus, etc. And of course, this is just 5. Now you're going to say, how is that legal? Well, it's legal because we know sine of x is equal to its Taylor series, centered at 0. We know that. And since the limit's at 0, that's perfectly fine.
You go back.
Yeah, I sure can. Now, again, you're not going to see these patterns as quickly as I am, but that's, you know, some of this, the learning has to be on you, right? You got to go home and suffer through the details.
Suffer.
Suffer, that's a good word. Suffer is good. There's no, what's the old saying, Emily? No pain, no gain, right?
Yeah.
What did you say yesterday? You studied for 5 hours and you know nothing?
Each test.
Each
is
test.
5-hour study session.
So
So
you guys are
that's
doing it
just
wrong,
the
though. You're doing it wrong. You're supposed to study every day so that you don't have to cram. That's right, Eric. There's always pain. It's very true. So this, yeah, we're gonna get there, Becca. That one's the brutal one. There's a cute little trick you can do that I just alluded to, by the way. Maybe you can figure it out before I get there. Why was this legal? Because since we're taking the limit at 0, we can use the power series because we know, or the Taylor series, whatever you want to think about it. The problem with 5c is the limit is not at 0. The limit's at infinity. So you got to be very careful of what you do. The power series, that idea is not going to work. 30 derivatives a day. You know what they say, 30 derivatives a day keeps the doctor away. That was a stupid joke. Well, didn't they, when you're a kid, they tell you to eat apples or something, right?
Yeah.
I'm not even convinced apples are healthy. I'm not.
Why?
I don't know, because I always say and I don't know, I know this is calculus, but we're going to do 5C in a second, but they always tell you to eat things that there's no way people ate 100 years ago, right? Like they'll say you should eat all these fruits and vegetables. Well, if I lived in Pittsburgh 150 years ago, guess what I ain't eating in November? Fruits and vegetables. Where the hell are they being grown at? Right? Who's growing bananas in Pittsburgh? Do you understand what I'm saying? So I always figure you just got to eat what your ancestors ate. Now you're going to say they died young. That ain't necessarily true. Because what you'll say is, well, the average life expectancy 100 years ago was lower. Yeah, no poop. You know why? Because 100 years ago, a hell of a lot more people died young because of diseases and stuff. That didn't mean no one lived to be 80 or 90, right? And I remind myself, most of the humans on this planet don't understand the difference between mean and median. And that makes me mad too. That's why everybody should just study math all day, every day. And we would have no more problems, right? I'm telling you, man. Anyhow. All right, let's look at 5C. So the trick for 5C is to do a substitution. So the trick is to set t equal to 1 over x. Okay? Thus, the limit as x goes to infinity of 1 over x is the same as the limit as t goes to 0 of t. So think about this for a second. If x is going to infinity, 1 over x goes to 0. Now you're going to say, how can I do this? What do you mean? You can change variables anytime you want. It's not illegal to do this. The only time it's bad is if you're not bad. The only time you have to be careful is if you're going to start either integrating or differentiating. Then you have to be careful with how you switch variables. Of course, we know how to handle that. We know when you're differentiating and you switch variables, there's this thing called the chain rule. And if we're integrating, we have to use integration by substitution. But we ain't doing that here, right? We're just taking an expression and rewriting it. Okay. Both of these things equal 0, right? So then what is x e to the 1 over x minus 1? Well, this becomes 1 over t equals, oh, excuse me, this is 1 over x, sorry. This is 1 over, I'm losing my mind, honest to God. You guys got me all mad about math education. No more. So 1 over t e to the t minus 1. Okay, so what does this mean now? Well, now we can just write out what is e to the t? E to the t is 1 plus t plus 1 over 2 factorial for you, Shobit, t squared plus 1 over 3 factorial, t cubed, etc. And then that's minus 1, right? So I did that for you, Shobit. You sure you don't want me to write 1 over factorial and then 1 over 0 factorial? Now, I should do that, honestly, because I keep forgetting that you guys are amateurs. You're babies. And then you're probably confused because my T's look like plus signs and context is in. Oh, my God. Settle down. I know. I should have used a different letter. God forbid. But look what happens if I distribute now. Remember our old friend distributing, I'm left with, well, first off, 1 cancels, right? So this is the key observation. This 1 and that 1 cancel. So what you're left with when you distribute, remember that, the old distributive law, boop, 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 all the way down. So what you're left with is 1 plus 1 over 2 factorial t plus 1 over 3 factorial t squared dot, dot, dot. And of course, if t goes to 0, this goes to 1. So that's how you do that problem. Any questions about this? Becca, you asked. Do you have any questions? Not to pick on you. Well, everybody can see the chat anyhow. It's common knowledge. Yeah, but you can see it here, right?
But like on Zoom.
But it doesn't show it on Zoom.
Well, I guess I mean you can go in your own chat, but.
Yeah, right. I just think I deleted it. That's a good answer, Becca. Yeah, it is. This stuff is not easy. Come on. Look, that's the thing you got to remember too. It's not easy. This particular one, 5C, is not easy. But the bigger picture is replacing things like sines and cosines and exponentials and logs. Replacing them with series can make calculations much easier. Now, of course, you're going to say easier. You don't get it, right? You're just learning. Excuse me. So it's not easier to you yet, but it is. And it's also, for those of you going in the physics classes and in engineering classes at some point, this is a very, very common technique. We replace ugly functions and expressions with polynomials. So we're going to show you exactly what that means in the next problem, which is C. So part C is an extreme, or excuse me, 6, not C. Problem 6 is a great example of how we can take messy, avoid difficult computations. All right, so let's go to that. So series are useful for approximating complicated integrals. So I'm not going to do the one on the homework, but we'll do a similar one. So let's say we wanted to integrate from 0 to 1 of, how about e to the x sine of x dx. Now, you might remember from earlier in the semester, this integral can be computed exactly, but it's a very tedious integral to do. Now, of course, I understand you can look it up or you can plug it in the software, and that's fine. But then when you do that, you're missing the beauty of how we can approximate things in general. So the first thing to note is a direct evaluation is very tedious. So that's one thing. And the other thing is, even though a computer can help us, let's approximate using series. So what do I mean by approximate? Well, we're going to go to Desmos, and then we're going to have to do this quick because we're almost out of time, right? I think, what time are we done? 12:35? 12:30? Not 45. No, it's not 12:45 because we started at 11:50, right? So we're supposed to only be 45 minutes. So it's 12, yeah, 12:35, right? That's the rules of the Roni. We're only supposed to be here. That's what I'm telling you. I didn't make it up. Look at this guy. No, it's ridiculous, but it is. I shouldn't say it's ridiculous. What am I? I'm being disrespectful for people. I know I'm being disrespectful. All right, so let's look at this. What function are we interested in? We're interested in e to the x sine x, which looks like this. Now, we're only interested in what's happening between 0 and 1, correct? So let me show you the area that we're interested in. We're interested in 0 less than equal to e to the x sine x. I guess we should put a y here. And we're interested in this area between 0 less than x less than. So we're interested in this. I'm going to change the color. I'm going to make it red. We want to know this, the integral here that's going to, which will give us this area, correct? Right, so let me change my scale a little bit just so it's a little less daunting what's happening. All right, now, what I want to do is I know that this integral requires 2 integration by parts. It's challenging. So instead, I'm going to look at Taylor series, but I can't use the whole series because that seems ridiculous. So what I'm going to do is I'm going to pick off the first few terms of each one. And I'm going to use Desmos to aid on how many terms I think I need for a good approximation. So for example, let's put parentheses here and here. So the first thing I'm going to do, let's do the first 2 terms of e to the x. We know that its Taylor series is 1 plus x, the first 2 terms. We know the sign is x minus 1 divided by 3 factorial x cubed. So I need an equal sign here. And so let me get a different color, green. So what I notice right away is this approximation is okay, but it's not great. It's not, the area under this green curve is, I'm missing a lot of stuff here, right? So what I ask myself then is, okay, what if I do another term? What if I put the plus 1 divided by 2 factorial, which is still 2, x squared, and then I add the next term here, which would be plus 1 divided by 5 factorial x to the 5th. And now my approximation has become slightly better, right? I'm only missing this portion. Do you understand what I'm saying here? So I can use, and by the way, there's much more sophisticated ways to determine how many terms I should use, but we can't teach you them in this class. But I can sort of reason it this way, right? So and maybe I go another term. Maybe I go, okay, plus, oh, yikes. You know, let's go 1 divided by 3 factorial x cubed. And so now I'm feeling good about myself, right? And by the way, maybe I don't need all these terms in the sign because these terms in the sign are going to be much smaller. Power 5 is going to be, right? Is it going to contribute as much as power 3? Well, the answer is no, because remember, I'm between 0 and 1. So maybe I don't even need this term. And see, that's still pretty good. So maybe I only need the first 4 terms of e and the first 2 terms of the sign. Do you understand what I'm saying? All right, so what I'm going to do is I'm going to do that. I'm going to say, so, and by the way, let me show you something. What, maybe I don't even need the first 2 terms of sine. Maybe I only need the first, right? Now that's not great, but it's not terrible either. Do you understand what I'm saying? Okay, so what happens if you just use the first there and then get rid of one of these? You say, oh, okay. What if I get rid of these? Well, now I'm in a line, right? Do you understand the game I'm playing? Okay, so very good. Well, So what we can do is, so we might replace e to the x with 1 plus x plus 1/2 x squared, and sine of x with x minus 1 over 3 factorial is 6. So we might do that. So algebraically speaking, this is not much fun, but you can definitely multiply it out. If you wanted to. So I shouldn't say this is equal, this is approximately. And then if you multiply it out, you're left with x minus 1/6 x cubed, and then it's plus x squared minus 1/6 x to the 4th. I'm just doing algebra. And then it's plus 1/2 x cubed minus 1/12 x to the 6th. So, or not 6th, 5th. So I just did algebra. I distributed, wrote everything out. So the first term is x, and then 1/6 x cubed, 1/2 x cubed. When you get a common denominator, that's 3/6. So this becomes plus 2/6. Yes.
What's that last?
This thing,
Yeah.
it's minus 1/12 x to the 5th. I'll clean that up for you in a second. That was ugly. I'm sorry. Yeah, that was bad, right? So I have this polynomial, which is much easier to integrate than the function e to the x sine x. That makes sense? So look, if you integrate this, and we're out of time. And by the way, this one just had ugly polynomials, but the one on the homework, for instance, 6 is not as bad as this. It's actually quite, it's easier. What's this integral? Well, you're evaluating these from 0 to 1. So you get 1/2 plus 2 over 24 plus 1/3 minus 1 over 30. And then 6 and 12 is 70, right? No, 72. Which one did I forget? When I integrate 1, I get x squared over 2, so that's 1/2. This becomes 2 over 24. This becomes 1/3. 5 and 6 is 30. And then what's 6 and 12? Well, 6 and 10 is 60 plus 12 more, so 72. I got to go to a calculator for this. Not in my head. No, I can't. Can you? There's probably some people out here in this world that can, right? What's that again? He might be able to. He's good with it. What happened to my num lock? Who turns the num lock off? Who? I don't understand who doesn't need, like, I don't get who doesn't like that. Does it? Why would I want to do that? Who would want to do such a thing? By the way, you could see we don't even necessarily need all these terms because what are we really contributing at the end? 1 over 72 is not really contributing much. Anyhow, if you get this, you get that this is approximately 0.869. And by the way, the actual value of the integral is 0.9. So the fact we're saying is we're, depending on how accurate you need to be, this gets the job done. All right, any questions about this? We're out of time. All right, listen, if you have questions, please email me, send me an email or whatever, let me know. Bring questions on Tuesday. Thank you guys very much. I will see you all on Tuesday. Have a good weekend. Be careful, be safe. Thank you, bye.